All right. Welcome, everyone. My name is Cong Wang. I am a co-PI on the Fabric project. Thank you all for joining us today for the fourth installment of our Stitching Together Innovation with Fabric Users webinar. Today we'll be featuring Mariam Kiran, Cong Wang, and Imtiaz Mahud. Next slide, please. Before we begin, I would just like to share a few housekeeping items. The webinar will include a live question and answer session right after the presentation, but please note that the chat features has been disabled. So if you have any question, please type it into the quick Q&A box at the bottom of your screen, and we will answer it during the Q&A session. And also, the webinar will be fully recorded, and it will be shared with all the registrants after. Next slide. Yeah, great. Today we're joined by presenters Mariam Kiran, Cong Wang, and Imtiaz Mahud. Mariam, Dr. Kiran is a co-PI on the Poseidon project, leading the networking tasks of the project. She is an AI scientist working in computer networks and currently leads the Oak Ridge National Labs Quantum Networking Group. Her research explores machine learning and decentralized optimization for wide area networks, wireless, and cloud infrastructure needed for building self-driving networks for improving network performance, flexibility, and high-speed distributed data transfers for science workflows. She received her PhD and master's degree from computer science from University of Sheffield, UK, respectively. Cong Wang is a senior computational network system researcher at RENSI. He conducts research on cloud computing, networking, and machine learning for distributed systems. Finally, Imtiaz Mahud is a network researcher focused on developing intelligent and efficient networks. He earned his PhD and master's degree in electronics engineering from Kyungpook National University. From 2019 to 2022, he worked as a postdoctoral researcher fellow at Kyungpook National University. And since 2022, he has been a postdoc scholar at Berkeley Lab. His current research interests include artificial intelligence, 5G, multipath TCP, TCP congestion control algorithms, edge computing, and quantum computing. And now I will pass on to Mariam to start the presentation.
Okay. Thank you, Casey. So welcome, everybody. So Casey did a great introduction for all three of us who are going to be presenting. We have been doing a lot of interesting TCP experiments on Fabric. So we're going to be describing to you how we did that. So this is the agenda we will follow for today. We'll start off with why do we do TCP research to begin with. So we worked with large science transfers, particularly in the DOE network system. And a lot of this project was, this work was funded via the Poseidon project. So we have a few slides which talk about what Poseidon actually was set out to do. And then we will go into actually building up our experiments on Fabric. So we talk about some of the Fabric resources we use, what are the Jupyter notebooks we designed, and all of this is code that is also available to you guys so that you can try it out on your own. And in the end, Imtiaz is going to do a live demo of actually setting up these experiments and showing you how TCP experiments are done. Next slide, please. So we start by talking about why do we want to do TCP research to begin with. So in science transfers, you can imagine that that CERN runs and it produces a very massive amount of data sets. So these data sets could range from 8 gig to 10 gig at a time. And then you want to transfer those files across to the other scientists to actually do research on them. That means the network becomes a very important part because you're not going to be sending the data over AT&T or those kind of commercial networks. You'll be sending it over DOE's own internet or own networks itself. So that means we manage all the resources in the middle, which includes the routers, the switches, the cables, etc. So we can actually do very intelligent stuff on the network to make sure that the data transfers happen very efficiently. So in science, we have particular needs for our data transfers, such as they have to be efficient, they have to be timely. If you're transferring a 10 gig file, you don't want to wait 3 days for it to be finished. So we can optimize the network to make sure that it's finished within a few hours. And a lot of this can be impacted by what kind of protocols you are using in the network, such as TCP. So the way TCP works is that it does a three-way handshake. So here we have a sender and a client. So before a transfer happens, the sender sends a sync request to the client, and the client sends an ACK back. And then the sender says, okay, I've received your thing. And once this three-way handshake has been established, that's when the sender will send the rest of the file. So this adds a lot of reliability to the data transfer and makes sure that none of the packet is lost during the transfer happening as well, which is very important for science. So this is where networking research comes in, where we can design our own protocols. We can make sure that we can track if something has gone wrong on the network. So even before the scientists know, we can know if something has gone wrong in the transfer also. And a lot of the networking researchers over the years have designed their own congestion control algorithms, such as Cubic, Reno, Hamilton. The most recent one is BBR, which Google has designed to help improve the video quality of, say, YouTube running and sending files across. So that is specifically being designed for video so that the file performance does not get impacted by any packet loss happening on the network. And then there's also the way you manage the flows coming into the router, which is called buffer management. So you can have very intelligent queue management techniques also done over there to optimize the performance of the network. So one of the motivations for this particular research was that we know that in real world, as we use our science networks, one network link will have more than one flow in it. So you will not just have one flow going in at one particular time. So it's kind of like a road where you have multiple kinds of cars on the road at that time. So all the cars have to share the road at that time. And we want to make sure that all these TCP congestion control that is on the network are sharing the files equally, and that not one is taking over the rest of the network. So this is shown very nicely in this particular graph chart by Ripe Labs over here, where initially the network starts by running a cubic transfer happening from the sender to the client. And then after some time, BBR starts. Now, BBR does not play fairly. So what it does is it takes over the whole of the network link and really congested or chokes the cubic flow that was running there before. So you can imagine the person who's waiting for the cubic flow to finish is going to be very unhappy by the end of this. Until the BBR finishes, they won't get any of their file transfers. So this is actually the motivation for this work. So how can we recommend to the science networks that these are the congestion control algorithms that you should be deploying to make sure that everybody is getting a fair share of the network and not one of the person is overpowering the other people in the network. So as part of the study, we analyzed different kinds of TCP congestion control, which Cong and Imtiaz will talk about. And we particularly focused on big file transfers, such as elephant flows, which we call them. So these are very big file transfers that you have to do within a limited time period. Next slide, please. So the way we design these experiments is a typical bottleneck topology. So you have senders at one end, which is connected to one point, and that is connected to another point. So there's just one link where you can create a bottleneck, and those are all going to the receivers at the other end. So at the bottleneck link is where you can deploy all of your monitoring tools to make to catalog how the network protocols are sharing that particular link. If one protocol is taking over the other protocol or not. So you basically do a lot of monitoring on the bottleneck link, and you can control how the experiment is doing. And this is how we set this topology up on Fabric as well. Next slide. So I mentioned that this work was funded via the DOE-funded project Poseidon, which was a collective project with USC, University of Southern California, RENCI, ORNL, and LBNL as part of the team. And this particular project was designed to improve the quality of the DOE science workflows. Now, we know that DOE science workflows are distributed in nature, where you have detectors at one end, doing compute at the other end, and then actually doing some other analysis at the other end. So these workflows are geographically distributed across the US. And we were interested to find out if we can detect anomalies or diagnose anomalies and actually improve the performance of these workflows as the science is happening. Because we don't want a workflow to happen and then the scientists figure out, oh, something went wrong, so they have to redo the whole experiment. So Poseidon had concrete goals on how we can build a platform and make these services available to the scientists so that they can predict the performance of their workflows, detect and classify any anomalies happening, and also optimize the performance of the science workflows also in terms of compute and network so that they can get better science out of it. And I would like to pass this now to Cong to cover the rest of this.
Thank you, Mariam. So the Poseidon project lies in 5 different tasks. So the first task is to acquire diverse datasets from various workflow executions, both on the testbed environment, such as Fabric or Chameleon Cloud or Cloud Lab, or from the real DOE computational and data infrastructures. And Poseidon provides a set of mechanisms to predict the workflow performance. So we aim to find the early signs that can lead to the workflow failures, so that instead of waiting for several days for the workflow to finish and realize that the workflow has somewhat failed in the middle, we, like the scientists, can stop their workflow and rerun the workflow at the early stage. And also we perform various machine learning mechanisms to aim for the anomaly detection for the workflow execution. And we also perform a set of measurement study to guide the performance optimization for for the workflow execution or for the infrastructure to be improved for better performance for the science workflows. And finally, we provide a set of evaluations, methodologies to evaluate the various metrics for the workflow execution, as well as we provide dashboards for the scientists to observe the workflow performance. So next slide, please. So in this talk, we are focusing on the network aspect for Poseidon project. We are focusing on the measurement study for the network performance analysis and for the guidance for future optimization. This is mainly because data transfer is an important aspect for distributed science workflows. And we have run extensive initial experiments showing that we were not able to get the expected performance out of the science workflows. And we found that the conflicts and the background traffic or as Mariam mentioned, that multiple flows within the same network channel can cause significant impact for the data transfer performance. Therefore, we conduct this TCP research to quantify the network performance and the network traffic that are happening within the science workflows. And also we use measurement study to build characteristics on how we can get optimal performance when there are more than one workflow or more than one data flow that exists within the network channel. Next slide, please. So why we use Fabric for conducting our experiments? So this is mainly because Fabric's resources align well with our goals for performing our experiments. So Fabric provides a set of like variety of compute resources such as CPUs, GPUs, FPGAs, or persistent storage for us to perform our compute tasks. Also, Fabric provides a variety of networking resources, which we care a lot more. Fabric provides the programmable network infrastructures such as P4 or OpenFlow, and Fabric provides a variety of edge and core networks elements such as 5G, IoT capabilities, and also Fabric is a geographically distributed testbed that allow us to obtain resources within the different Fabric sites, so we can have like experiment results that are closer to the real life scenario. And also Fabric provides facility ports that can connect to other testbed or services such as Commuting Cloud or Cloud Lab. More importantly, Fabric provides high bandwidth links across the different Fabric sites so that we can perform the realistic data transfer experiments that for the large scale workflows and the high throughput data transfers. So next slide, please. So what we are doing on Fabric, our goal is to improve the network performance for science data transfers. And we consider, as Mariam mentioned, we consider how the TCP congestion control algorithms and as well as the active queuing management algorithms affect the performance for the network data transfers. We seek to evaluate the fair share of the data transfer when they are happening within the same network channel. And we aim to build data sets for the different transfer protocol behaviors, and we hope to lead to the new data transfer methods to better understand how the data transfer happens within the wide area network and how they perform in a realistic scenario that can be comparable to the real DOE science workflows. So next slide, please. So Imtiaz will give a demo of how we are performing the experiments, as well as on a tutorial on how you can also use our Jupyter notebooks as well as our experiment setup to try your own experiments on Fabric. All right, thank you.
Thank you, Cong. So I will dive in the demo section for today's session. Just to make things easy for everyone, that I would like to give this presentation pretty slowly, and especially I hope that this will be helpful for those who want to do the network research and they are just trying to start with the Fabric as a newbie. So I believe this session will be helpful, especially for them. So now for our notebook to be available, so if anyone can scan this QR code and have our notebook in their, they can see our notebook, or also anyone can go to this link and have the notebook in front of them. For these experiments, we actually are using such a topology, that is a dumbbell topology that we say in networking terms, where there are several senders like sender 1 and sender 2, and there are receiver 1 and receiver 2. So the senders, there are two routers in between. So the senders are connected to the router 1 and the receivers are connected to the router 2. So all the senders are passing their traffic through the router 1, and all the receivers are passing their traffic through router 2. So between them there is a single link. So in this network, we consider this link as the bottleneck link. So by this link, all the traffics are bound to pass. So without this link, if this link breaks up or if there is a congestion in this link, so all the traffic have actually fills that congestion or fills that network outage. So that's why we adopted this kind of topology in our experiments, so that we can see the impact of different TCP constraint control algorithms and also AQM algorithms, as Mariam discussed before. And for this experiment, actually, we used several TCP fabric sites, like the senders were set up in TAC, where the receivers were set up in Princeton, and the router 1 and router 2 were set up in GATTEC and Rasker. So you can see that there is a long line of connection, and the RTT was approximately 78 milliseconds between these two sites. So this is just a glimpse of what we are, what setup we are using for our experiment. Now I will try to give you some first, before going to the actual demo that I have recorded to show you that how we are setting up everything. I will try to give you some tips and tricks. Those will explain how are we setting up all the things step by step. So let's start by how you can reserve a node with some specific NIC address, specific NICs. So as you know that when you, this is the Fabric notebook that I have already shared. So if you go here, you will find some code like this one. So this code actually gives you the line of code that you can run and get the available resources in the Fabric. So it will give you a table with some resources like kind of this table, where you will see that what the site names are, how many cores are available, how many RAMs are available, what is the NIC available. This is the basic NIC, ConnectX-5 and ConnectX-6. So these are different kind of NIC. So NIC is the network interface card. So you know that whenever a computer or a device wants to connect to the network, it has to have a network interface card that allows it to connect to the outside world. So now Fabric offers different kind of NIC for the nodes that we get from the Fabric. So you can either connect to the basic NIC that has the connectivity like 1 Gbps or 10 Gbps, and then there is the ConnectX-5 that gives you a connectivity from 25 gigs, and there is also ConnectX-6 that even gives you connectivity to 100 gigs. So you have different range of NIC, but all those NICs are not available. Normally, the basic NICs are very much available, pretty much available for all the sites. But you see that ConnectX-5 or the ConnectX-6 are the high demand NICs, so they are not always available. So whenever you are going to set up your own experiment, and if you want to go beyond the 25 gigs, so you will need ConnectX-5 or ConnectX-6 NICs. And for get those, you first need to go through the sites, like which site have those available, and they also require your RAM and the cores, right? So you also need to check that how much core you need and how much RAM you need, and are they available or not, and then you can go and take the node. So here is just a simple case that how you can select the NIC. So you can just add a component as a NIC, and then in the NIC you can in the model you can select that NIC ConnectX-5 or ConnectX-6 or NIC basic. So you can select the model and you can then take the NIC. So that is basically how you can take a NIC. And then there is also I will go inside that how to create a dumble network topology. So as I have already mentioned that why we need the dumble network topology because we wanted to have the traffic going through a single link, so that there is a congestion. If there is a congestion, it happens here, we can measure everything. And even if there is a network outage, so that we can also measure from there. So for that, to create such a dumble topology, you will have to follow some specific or several steps. So I would try to break down in it some steps. Like first, we need to get the node that we are. I believe that most of you already know that how to get a node. So in the Fabric, you can just take a node like add a node like the add node command, and then you are going to add a component like if you want the basic need or ConnectX-5 or ConnectX-6, so you can add those as a component there. So To set up a host, what we are trying to do, what we are doing, that we are first taking a node and then we're adding a component, and in the component we are fixing that we are taking it as a NIC, and the NIC component is a NIC connect 5. And then we are also saying that to get the interface. So when you are getting a NIC, and then you are also getting its interface. So a NIC can have multiple interfaces, like so in Fabric. So you can get here. I am getting a NIC with a single interface for host one, because the host one has a one connection with the outside world, and whereas in the same way the host 2 has also one connection, host 3 and host 4. That is, all of them has the one connection. So all of them are following the same command. Same line of code to actually add the NIC. Now to set up the router. To set up the router, there are several more steps to follow. For example, we are again taking the node as the router, and then we are again adding the component, like similarly added for the host 1, host 2, and then in the component, so we are taking a component like h1, h2 NIC. So for example, for both these two, I'm taking a NIC that is h1, h2 NIC, and in that NIC, I'm actually taking two interfaces. So interface 0, interface 1. So I am dedicating each interface, for example, R1 interface to H1. So this interface I'm dedicating to this H1 device, and the other like R1 interface to H2, I am dedicating to this H2 NIC. So I'm taking a NIC and I'm giving the interfaces of that NIC, dedicating the interfaces of that NIC for this H1 and H2 host, and to measure the to connect the router 1 and to router 2, I am taking a separate NIC, so that I can, if I want at some stage that I want a different NIC, like connect a 6 NIC here or a basic NIC, and I want to see that what happens, or if I want to change the equivalent algorithms inside this NIC address, so I can do that if I have a separate NIC. So that's what I am trying to do. That's what we did. So we took a separate NIC for dedicated for R1 and R2. So that's what we're adding here as a component, another Kinetics 5 NIC. And then I'm also taking the interface. So because it is only connected to the R2, so we need only one interface. So that's what I'm taking, like just one interface. In the same way, for the router R2, we're also taking two interfaces, one Kinetics 5 here, and two interfaces for receiver 1 and receiver 2. And then we're also taking another Kinetics 5 dedicated for the R1, and we're taking the interface like connecting for the here for the R2 interface to R1 to connect to the R1 router. So now we have the interfaces ready, but they are not connected till now. So we want to create a physical connection between them. So in this step, we're actually connecting them physically. So we are using the L2 network command. So by this, in here, I'm giving them the interface name. So by that, they are actually connecting the NIC. For example, like here, R1 interface to H1, this NIC to H1 interface. So there it is making an L2 connection between these host H1 and the R1. And in the similar way for the H2 R1, we are also making the similar connection. So by taking this L2 network, so we are creating an L2 network connection between the interface host and the routers and the event of the routers. How you can actually network between the routers and between the hosts. So as I mentioned before, just to repeat, here you are creating, you are making available the interfaces. And by this command, you are actually connecting the interfaces with the L2 network. Then, so right now we have a physical connection between the interfaces or between the nodes. And now we need to make a logical connection. So that's the next step where we actually set up the routing table. We are going to set up the logical addresses to them. So here is how you can configure the logical addresses to the routers, and then also to the sender or the receivers. So for the routers to set a basically, I believe that I should first show you the sender or receivers that you are going to set up the physical addresses for them. So here first you take the same interface with the get interface command and passing through by the interface name that we already gave here. For example, you see here we gave the net h1 r1 name. So this interface name you are going to just pass to the get interface command, and then it will give you the interface name, and you need to with that you need to get the interface name from the command line. So actually what is happening, we are actually going inside the Linux kernel that we have in the VM. From the Linux kernel, we are getting the interface name of the exact interface name that is connecting host 1 to router 1. So by this command, and then we are going to make a physical connection, logical connection there. So by this, we are trying to link, we're setting up the device app by this command. We are executing this command in the Linux kernel. So we are actually setting up the first setting the device up. Then we are also setting the MTU size to the maximum 8900, and then we are assigning it with a physical address. So we are assigning it as a physical address, logical address like the 192.168.2.2. So we are creating a separate network here. And then I am also getting it, telling it that the AQM algorithm that it is going to use is the FQ. So you can also change that one. And then it is also telling it that the pseudo IP route, that is if you want to route a packet. For example, if you want to send a packet to this receiver R2, so this has an IP address of 4.2. So when you are sending a packet to this kind of network 192.168.4.0 and so on. So in this network, if you want to send, so you need to route that packet via this address. So this address is basically for the router. So that is what is happening, that whenever it has some packets to transfer to any of the receivers, like receiver 1, 2, and even to the sender 2, so it will send all the packets to the router, and the router will know what to deal with those packets. So that's what it is saying to the that's how it is setting up the routing table. So basically this command is run with all the receivers, all the senders, sender 1, sender 2, and the receiver 1, receiver 2, and that's how we're setting up the network for the routing table. Then I'm showing you that how we are setting up the routing table for the routers. So here again, we're taking the same example, like we're getting the same network interface name, and we're going into the router's Linux kernel, and then we're setting up the we're taking that interface up. We're setting the MTU, and we're giving it a new network, that is the 1.1. So as you can see that for each of the routers, for example, this center 1 and the router 1, this interface belongs to the same network. So center 2 and router 1 second interface that belongs to the same network. So but both of them are separate network, like it is 2.1 and this is 3.1. And there is also a separate network between the routers, like router 1 and router 2, that has a 1.2, 1.1, and 1.2. So that is the 192.168.1, and this also has the 192.168.1. So they have the same network. And again, we're having separate network for this and separate network for this one. So that's what we are trying. We are actually giving them the information into the router, that the router, you are connected to this part with this network. So that's how we are connecting it, that you should have this network IP. And then we have a second network IP for connecting to the center 1. We are giving it here, and then we are actually giving it a third IP to connect it to this network. So a separate network IP with a separate network. So that's what we are giving here for the router 3, a router to router connection. And then we are actually executing a route command that whenever you have a packet, for example, for this specific network, like 1.2. So then you actually forward this packet to the if you have a packet for the 4.1, 4.0, or 5.0, for example, for this the receiver 2 or receiver 1 or receiver 2, then you forward it to the 192, the raw 68 port. So you are forwarding to the router 2. So I am actually letting the router know that you have to forward the packet to router 2 in order to pass the packet to the receiver 2 or receiver 1. So that's how we are actually setting up the network and also letting the networks know each other that how to route the packets. So the same kind of command is also executed in router 2, and it sets up the network by following those commands. So we have by executing this command, actually we are having the logical network ready. So now we have previously we had the first interfaces, then the physical network, and then we have the logical network. So if you do the ping, then you can get the ping from the host to from end-to-end connection, like the host from the sender to receiver. Now, one more important thing when we were doing the network experiments, that if you use the traditional iPerf that we are getting from the Linux kernel, so that iPerf cannot utilize all the threads available. So that is not a multi-threaded iPerf. So ESNet has developed another iPerf 3 specifically. Actually, this is modified by ESNet. So that iPerf, it can actually use multiple threads altogether. So all the available threads, it can execute all together. So by that, so this is very important when you are actually trying to go beyond the 25 gigs or something like that. That is high data rate. So in those kinds of scenarios, if you are going to use iPerf for the data generation, so iPerf should have to utilize all the threads to generate that much of traffic to populate the network. Otherwise, if it is using the single threaded one, so it cannot generate that much of traffic. So that's why we recommend that you use the iPerf 3 from the ESNet. That's what we used here. So we actually basically made a script that iPerf 3.sh. Here we download the iPerf from the ESNet and just enter it and then just install it. So to such script you can make. You can also upload those scripts to the public nodes by such kind of command, and then you just run that script in the fabric in the specific node that you want to run by executing this kind of codes. Finally, and workaround I would like to share that helps us avoid any infinite link or hang up in the process. So what we try to do when we're experimenting with the different scenarios, all these experiments were actually pretty much of taking a long time. So even our experiments run for several days. So what happened that when we're running some experiment for several days, if for some reason some script that we're running hangs up or have some error, all the experiment pauses. It holds there. So to avoid such kind of scenarios, we developed this kind of a code snippet here. And I believe that it might be helpful for anyone else who were trying to do such kind of automated experiment and try to avoid hanging up frequently, which when we're actually executing multiple scripts. So by this code snippet, you are actually giving the command and also giving a timeout time. So with the command, so it is actually, for example, if you have a command to run, or if you have a script to run, so you run the script and it will check for the timeout time, that if the timeout has occurred. So by the time of time, if the script has not stopped, then it will forcefully stop the script and go on with the next execution. Otherwise, in the other way, if the script has already stopped, then it will simply go to the next line of code. So by that, you are actually avoiding, you can avoid a looping, or you can avoid hanging up for some script and waiting and having disruptions in your experiments. So by that, I am actually finishing the tips and tricks sections. Now I will go into the demo. So before going to the demo, I would like to mention that the demo actually I am showing you, it is based on the slides that I have we got. from before preparing for this. So these are these slides that are in the demo. I will show you will we will create this environment. However, when we did our actual experiments, so we had different access to different slides, so different sites. So these are the sites that we accessed for our experiments, like Clemson, Washington, NCS, and TAC. And we had also access to the connector 6 router connecting the router 1 and router 2. So that gave us an access to go beyond 25 gigs. So we could go with the Kinetix 6 and by using Kinetix 5 for the rest of the network. So, but we for the demo, we are going to get into the slides that we could get just for the preparation of the demo. And for the experimental configurations that you will see that we will have different function control algorithms like we got V1, V2, V3, STCP, and qubit. Also, we have the EQ algorithms like P4, SQ Codel, and D. We also have different BDP, that is Q length based on the BDP 1, 2, and 4. And we also have the bandwidth at the bottom, like different bandwidth like 1, 10, 25, and 40 gigs. We actually parallelized the flows for each of the bandwidth scenarios. Like we had 25 hyper processors per node with 10 parallel flows for to reach the 40 gigs scenarios. So that's actually we did this to so that we could we could utilize the entire bandwidth that is available to us. So for running the demo, I have already a video recording, so I will go into that. So if you see here that we are actually running the same script that I have already shared. In the script, we are going to have this gives us the glimpse of that the table that shows that what are the Kinetix NICs available or RAM available or the codes available that you can see from here. And then this line of code we have also added in the notebook where you can run and see that if, for example, a site has the Kinetix 5. So, for example, we are checking that if a site has at least more than one Kinetix 5 and a core available of more than 150 and a RAM available of more than 300. So by that, you can actually sort out the sites and see the site in such a list, and it makes things easier for you to find the best site suitable for you to set up the experiments. So in the same way, you can also run like to see the sites available with the 6. Then actually we go inside to so here I am showing like we are trying to take the sites that are based on Raja, so that we have a line of sight between the TAC, GATEC, Princeton, and the Raja and Princeton, so that there is no going and backward, so that we get a full line straight line, so that we have the minimum amount of RTT possible. So that's why we try to select the sites in such a way. So this is some tweaks that you can do in your experiment, like if you want some higher RTT link, so you can set the take the sites from distance places. So if you want to keep the RTT lower, you can keep them closer enough. So that will give you access to reduce RTTs. And then we are going inside this line of code of site where we are actually setting giving the slice name, then giving the router name, and setting the number of router cores, and giving the name for each of the network that we are going to set. I have already explained those things, and also we are setting the cores and RAMs and disks for the hosts, and we are setting the name of the router sites here. And we are also using the Ubuntu 20 as the operating as the ways for the nodes. So to go inside, then we actually can run the next slide that actually gives the create slide, this course next slide, and you can actually, this will start creating the slide. So for example, after running that slide, it takes some time. For example, about 10 or 12 minutes to create a slide. So you will get a stable slide notation, and you will get the management IP from this table. And so you can take the management IP and actually do SSH to the with the management IP, so that you can access to the node, whatever node you want. You can just access it and see that if the node is available or not, just to double check and to get access to the command prompt. And this by this running this setup NVMe drive, so you can also do some add some extra hard drive that if you want, so that could gives you that access. And this code snippet that gives you access to install the multi-thread iPerf3, and then we can move forward because I have already explained all these things. And now this is the Beaver v3 that we have a separate Beaver v3 script. So if you want to use the Beaver v3, then you can install, upload this script and install the Beaver v3 by running this script. It is very simple. So you can do that, and when the script is running, you can even go inside the CMD of the nodes and see if the scripts are running. And then you will need to reboot, and then you need to also configure the router. So you are just running those codes, and when you are configuring the routers, I will also show you one thing that you can run this line of code that is systemctlnet.ipv4.tcp constant control algorithms available. So this will show you that what are the constant control algorithms available, like Beaver. This is the Beaver v3 in this kernel. So this is Revenus Beaver, then Beaver v1, Cubic, but it also has the HTTP that is not here. To enable the HTTP, what you can do, you can just run this code. You can access the systemctl.conf file, and there you can, in the constant control algorithm setup, you can remove it by HTTP, and then just run the systemctl-p, and that will actually again default to the HTTP, and all the constant control algorithms will be available. So that is another trick that you can use to see the available constant control algorithms if you want to do some experiment with the constant control algorithms. And then the rest of the script are pretty simple, that you just go run those scripts, and they will give you some access to run they will actually just automatically run the experiments. And finally, finally, when you want to run the test, so you can run the for example, I have a separate set for FIFO test, FQ test, and RED test. So you can run either one of them and see the experimental results there. And after the experiment, there will be several tar files, several files created, and you can actually download those files. So for example, here I'm showing that there is the output directory file. There are several files are creating for each of the experiment. There is a separate directory for each of the experiments, and you can access those files from there. Now to download those files, you can just run this compress and download output this section, and this will actually make a tar file from all the outputs and download them. So that is a simple demo. I tried to make it short because I have already explained most of the things that you need to know before. So I will now just give you an overview of the results that we have experienced from here. So if you see that we have several results, we are getting an in-depth analysis from these experiments. We have the condition window, RTT, and also a probability that is taken separately from the script. So we are getting the RTT retransmission packets from the PCAP file that we're capturing, and also from the iPerf that we're running. So that is also giving us a number of retransmission packet and the consumption window. Also, we have the drop packets, some upper limit packets, those by running a script in the routers. So they are also capturing the router status. So for example, in the experiments, you can see that Beaver V1 is performing in terms of fairness better than Beaver V2 and Beaver V3 with a FE as the equivalent algorithm and with the 4 BDP of Q length. And in the overall impact of the RTT, Beaver has less impact and Beaver 3 has higher impact. In terms of retransmission, Beaver 3 has higher retransmission than Beaver V1. So this is all for the BFE4, but when we see the overall performance, we see that when we combine Beaver V3, as it is the most advanced algorithm, with SQCodel, that is also an advanced AQM algorithm at the router. So if we can combine both of them, then they provide the best balance of low retransmission, high fairness, and good throughput across all the scenarios in our experiment. So that is an overall take from all those experiments we run. That's the overall, that's a final take that we are also recommending to the DOE. So I believe I'm already overshooting the time, so I will not take any more time, and I will go to the question and answer sessions.
Right. Wonderful. So now we'll just go straight into the Q&A session. We'll start with answering questions that are submitted during the presentation. Let's see. The first question we have, isn't it the issue with fairness in AQM? For example, if we use FQ-Codel, it would be less likely to have this issue with BBR?
Should I answer the question? Okay, so yeah, so FQ-Codel and BBR plays a very good role. So when we are using FQ-Codel, BBR is most likely to have a pretty fair share. But it also comes, there are several other things that we are considering. So you are implementing FQ-Codel only in the router, but also in the both the host, you also need to have the FQ algorithm set it up for the BBR, and then it will have some good result. But just imagine that if you want to have FQ-Codel set up in each and every router of the whole world, that is not practical. So there are a few challenges involved in that. And so that's why even if you see to the development of BBR V1, V2, V3, they're all going toward making it less aggressive, making the BBR less aggressive so that it can accommodate some room for the other consumer algorithms in the real network, like the cubic and other consumer algorithms, because FQ-Codel is not too much common in the AQM algorithms. So definitely FQ-Codel can help BBR to have a fair share, but it is not the ultimate solution. We should be looking into some other solution also to make BBR itself fairer to the other consumer algorithms.
Thank you. Our second question here is, has there been or will there be any effort to extend the fair share concept to implement a pay per bandwidth condo model for network traffic?
So I could take that one and you guys can chime in. So that's a great question. This is something I've thought about a few times. So there is a lot of research in TCP and everybody wants to come up with their own model. There has also been some AI and machine learning implementations on, rather than using the traditional TCP mathematical equation, you could replace it with an AI and machine learning so it changes its behavior based on what is happening in the network. So I haven't found any examples where they've attached it to a cost per use model yet, but that's a good idea to explore. Maybe develop a new TCP that has a pay per use model. So that would be a good thing to explore.
Thank you. The third question, what are the most commonly used TCP congestion control algorithms in science networks?
So again, I can take that one. So because So we've been involved in this research for a few years, around 6 to 7 years, where we started this work with just analyzing pure T-stat data on the Science ESNet network. And we wrote a lot of anomaly detection algorithms to actually predict what kind of TCP is running on the network. So that is also open source code, which you're welcome to try. And in that study, me and Cong were involved in that study. We found that mostly commonly used algorithms were Hamilton on the Science network. And we found some evidence of Reno as well. But that was what they were transitioning into Hamilton because they thought Hamilton was the best to give them a fair use. So that's the most used currently, but they are investigating BBR as well.
Thank you. The next question, just to clarify, everywhere we have FQAQM, the link sharing on that part of the network will be more fair. Am I right?
Yes, as a brief answer.
Okay, that's a quick answer. Question 5. Do you also monitor other network performance metrics such as packet loss or delay?
Yes, we are also monitoring the packet loss and delays. So we are using iPerf tool to monitor the for the delay, and also for the packet loss, we are also recording the PCAP files. With the PCAP files, we are recording the lost packets.
That's great. Last question then. How are the network traffic generated? Do you generate the traffic following some patterns?
We are actually using the iPerf3 tool that I have already explained to generate the traffic. So it actually it depends that how many iPerf flow you are starting. Depending on that, the traffic is then generated.
Okay. Well, I think that's all our questions. Thank you. And now we'll bring up some of the closing slides. Thanks again for speakers today. And that's Mariam, Cong, and Imtiaz. And in addition to our presenter, we would like to also acknowledge there are several behind-the-scenes team members listed here who work very hard to bring this webinar to production. There's Casey Wang, Chelsea, Jayshree. So we work on the Fabric team. Next slide. Thank you to the audience for your participation today in this webinar. We will be recording this webinar and will email everyone who has registered with a list of resources. You can see that resources here. The slide deck will be shared, and then there will be a link to our Slack channel and Connect with Us forum. So we hope you will connect with us, with the Fabric team, for further questions and support. Our coming up next webinars are Mastering Fabric Tips and Trick webinar series on November 25th at 3 p.m. Eastern Time, and Stitching Together Innovation with Fabric Users on November 26th at 2 p.m. Eastern Time. So both webinars will be around the topic of facility ports, and the November 25th one will focus on existing Fabric users. The November 26th one will be focused on new users. We would appreciate it if you can forward this information to relevant users in your communities. And as a final reminder, please submit your Fabric matrix if you're a Fabric user, and make sure your project abstract in the portal is up to date, because we use this information for our outreach, including our website, to promote your research. And thank you again, and please have a wonderful day, everyone.